Um, we've been talking for a little while about solids and liquids, and now it's time to actually go into gases. You should be somewhat familiar with gas laws from previous chemistry classes, but we're going to go a little more in depth than in your previous chem class. Otherwise, this wouldn't be AP chemistry, now would it? So, first of all, for gases, the particles are spaced much further apart. So, you remember from Coulomb's law how distance is in the denominator and it's squared? As distance increases, attractive forces decrease exponentially. So, intermolecular attractions are minimal and are very minimized in gases, right? Now, when we're talking about gases, it helps if we know what pressure is, and pressure is force per unit area. And we measure atmospheric pressure with a device called a barometer. And a barometer is essentially a tube filled with mercury that's inverted in a pool of mercury. And then the height of the mercury in the column above the pool of mercury equals the atmospheric pressure that's pushing the mercury up against the vacuum in the top of the tube. And if you measure that height and it is 760 millimeters tall, that's 760 millimeters of mercury, which is 1 atmosphere of pressure. It's also called 760 torr, after the Italian scientist Torricelli, who invented the mercury barometer. Now, 1 atmosphere is also equal to 101,325 pascals, or 101.325 kilopascals. A lot of this information is found on your reference tables. So just look for that. The kinetic molecular theory is something that the College Board likes to get into a lot of detail about and ask you a lot of questions about. But it has several different fundamental assumptions about the motion and behavior of gas particles. Because kinetic means energy of motion, molecules. So this is trying to explain how gases behave. So, first, we assume that gas particles themselves are so incredibly tiny compared to the distance between particles that the volume of the individual particles themselves is negligible or essentially zero. So, in other words, if we have a container of gas, we say that the volume of these individual gas molecules is very small compared to the distances between the molecules. So the space that the gas occupies is so much larger than the actual volume of the individual molecules that we essentially ignore the volume of the molecules themselves. We also say that particles are in constant motion. When they collide with the walls of their containers, that generates what we call pressure. That exerts the force, and that force divided by the area over which it's exerted is pressure. Gas particles, we assume, do not exert any forces on each other. We assume there are no intermolecular attractions between gas molecules, that they neither attract nor repel each other. And we assume that the average kinetic energy of the gas particles, in other words, the average speed essentially of a group of them, is directly proportional to the Kelvin temperature. In other words, if you double the temperature in kelvins, you double the average kinetic energy of the molecules. And when the temperature reaches 0 kelvins, they have zero energy, so they would completely stop moving. Right? Now, when we talk about kinetic energy, there is a formula that says kinetic energy equals 1/2 mass times velocity squared. Now, what this would mean is that since temperature is a measure of average kinetic energy, particles that have less mass must be moving at a greater velocity. So, at the same temperature, hydrogen molecules would be moving faster than oxygen molecules because hydrogen molecules have less mass. So if they're at the same temperature, they have to be moving faster. And kinetic energies of gases are distributed according to a Maxwell Boltzmann distribution, which is a really interesting distribution. It looks kind of like this, where the average is right here. It's a distribution. It's not a bell curve. It is skewed to the right. If you were to increase the temperature at a higher temperature, this curve would look something like this, where the average would be here. And if we went to a colder temperature, then it would be more like this, where the average would be here. So we should label these axes. Your x-axis is going to be the kinetic energy, and your y-axis is going to be number of molecules. So what this is saying is that at a colder temperature, you have a larger portion of molecules with low kinetic energy, very few with high kinetic energy. As you increase the temperature, you have more molecules out here with a higher kinetic energy. The thing about this is if you're talking about the same sample of gas, the area under all of these curves, which would essentially give you the total number of molecules, is the same. Right. So let's check your concepts here. If the temperature of a sample of gas increases from 100 kelvins to 400 kelvins, how is the average speed of the molecules affected? So the temperature has gone up by a factor of 4. Well, if the temperature goes up by a factor of 4, the average kinetic energy has gone up by a factor of 4. So the average speed has gone up by a factor of 2. Because if we remember from the formula, kinetic energy equals 1/2 mass times velocity squared. So the speed goes up by a factor of 2. That's squared. The temperature goes up by, or kinetic energy goes up by 4. So temperature and kinetic energy are the same thing. Next, we were to compare the average speed of helium atoms to CH4 molecules. Helium atoms at the same temperature must be moving faster because they have less mass. Right? Now, an ideal gas, you might be wondering why there's a unicorn here. An ideal gas is one which perfectly follows the kinetic molecular theory. And ideal gases are the unicorns of chemistry. We can describe what an ideal gas looks like. We can mathematically model the behavior of ideal gases, but there's no such thing as an ideal gas because if we go back to our assumptions of the kinetic molecular theory, we assume the actual volume of the molecules is 0. Now, gas molecules are really small, but they ain't that small. They actually do occupy space. We assume that they have no forces of attraction or repulsion. If that was true, then no matter how cold the temperature got, a gas would never condense into a liquid because the particles would never stick together. And we know that that does happen. Now, for things like hydrogen and helium, which have very, very weak intermolecular forces, you have to get them really close to absolute 0. But water vapor, that condenses at 273 kelvins. Well, not condenses at it condenses at 373 and freezes at 273. All right. Because real gases, they do have finite volumes. They do exert forces upon each other. So when we start doing our mathematical modeling, it's not going to be perfect for gases that are real gases. And we'll talk about how those deviations come into play in tomorrow's lesson.